Okay, so this lecture we're going to take and build upon the previous discussion about building this large-scale intermodal supply chain optimization model for a large retailer, and actually talk to you about, now that we've built the model, what do we do with it? What kinds of things were we able to do? What kind of conclusions and analyses were we able to provide them with to show them value in applying these type of IE skills and techniques? So as a reminder, we're dealing with this problem of suppliers shipping goods to consolidation points, which are eventually destined for distribution centers. Some of the suppliers direct ship to distribution centers. We have different modes of transportation, different capacities, different costs, different locations, different distances, different times. These are all of our possible combinations, all of the possibilities. And the optimization study will be used to figure out, okay, I have all these options. Which of these combinations together are the most cost-effective, the cost-optimal, the lowest-cost solution, as long as I meet all of my constraints of satisfying demand, getting people the goods they need, etc. So some of the experiments that the client wanted us to run with our model was to say, okay, I want you to look at closing some of my consolidation points because maybe I don't need all 19. And if I close them, is it possible to save money? Because why? Well, I'm saving the operating expense, I'm saving turning the lights on, hiring the employees there. But closing them should also cost money too, because by taking that option out of our network, if a cost-optimal solution uses all 19, if I remove one of them, then whatever suppliers were shipping to the one I removed are going to have to ship somewhere else, potentially at a higher cost. Now, these closings could be due to low volume. In other words, we have this one consolidation facility, but it's really not handling that much. So what would it cost us to close it? But to trade that off, we wanted to look at this in terms of the fill rate. What percent of the demand requested by the distribution center does it actually get shipped to it? So I'm going to show you some charts that show different percentages. Our current baseline assumption is that we're meeting all of the demand. I said that in the last module. So that the DCs request X, they get X. So that their fill rate is 100%. Well, what if the DC only gets 99% of what they asked for? Or 98%? Well, if the DC doesn't get everything they asked for, maybe that means I'm shipping less. I could save some money. So with closing the consolidation points, I'm going to potentially have lower operating costs, but higher transportation costs, because now I've removed some options of where I can move goods. But how does that trade off with lowering everything that the DC wants? Because these shipments are being made to the DCs on a regular basis. If I only get 99% of what I asked for today, maybe tomorrow I can pick up the balance. And since this is all the network of the same company, their suppliers shipping to their consolidation points, shipping to their DCs, missing a shipment to a distribution center is being done by their own suppliers with their own goods. So it's called company internal, if you will. The company's responsible for the whole supply chain and all of the costs. So it's not like they're shorting an external customer. They're doing it to themselves for a potential cost advantage and trying to make it up in subsequent shipments. So we could close these consolidation points potentially based on low volume considerations. We could expand them based on the fact that I've got some stuff that's fully utilized. I'm at my limitations. And if I can expand it, would it want to take even more of my demand to potentially get me even better solution? Because in my current optimal solution, if a consolidation point's at capacity, that means we have fully utilized everything it could do in terms of pounds per dock door per day, or cube per dock door per day. So I have to ship anything else to the other CPs that have room. Well, what if I was able to expand them, add more dock doors? I want to see, does the model even ship more to it because it's in a really good location, or it's a cost optimal decision to do so. And furthermore, should I open a new CP in a different location based on the fact that I have an opportunity to better serve my customer, to better minimize my own costs based again on high volume issues? So we have the different data that we need. We've collected it, but how are we going to generate our demand here? Well, we got some example data for actual DC demand from each supplier, and we were able to use that as a satisfactory product mix, or a broad spectrum of what the DCs require from which suppliers. Client bought off on the data they gave us. So we took the first 4 months of the year, and we were able to look at an average of 81 million pounds of freight across all 19 DCs. Remember I told you before, we're looking at 6-month time horizon. So we were able to take the first 16 weeks and scale up the 81 million per DC, such that for the first half of the year we could generate an appropriate demand of 2.1 billion pounds. Large retailer here. So with this real data from 4 months, scaling it to 6 months, making logical assumptions, we were able to generate a 6-month data file that was representative of the different DC's demands from the suppliers. And interestingly, running this model, the model always seemed to hit the weight capacity, not the cube capacity. Now, if you think about the type of goods that a large retailer ships, maybe that makes sense, because more stuff they have is heavier rather than of high volume. So we're able to get the proper product mix and able to get the ability to generate this, the first 6 months of the year data file. So with this, let's look at some analysis. We look at all 19 of the consolidation points and figure out who's doing the least in terms of pounds. So in other words, this one consolidation point, 6910, was the 19th out of 19 in terms of how many pounds of freight it was actually handling. The 6911 is the 18th ranked, and so forth. So our experiments were, let's look at the baseline where all of the center points, all of the consolidation points, all of the consolidation facilities are in our network. And let's solve that optimally. Now let's take out the lowest poundage one, the least utilized. So that means we'll close 6910. There'll be 18 of them. Let's run that same demand profile, but with only 18 of them. As I mentioned, as you start to close down consolidation points, what's going to happen to your costs? Well, the transportation costs in our model are going to go up because there's one less option to do cost optimal routing. What's going to be balanced with that is what the company can save with regards to operating costs, employee costs at the consolidation facilities that they've closed. So at the 17 case, we closed the 2 lowest. At the 16 case, we closed the 3 lowest, and so forth here. So when you look at these results, you're going to see things in a very standardized way here. I'm always going to look at, if I'm looking at closing, expanding, or anything, I have to look at it in terms of the fill rate at the distribution centers. So I'm going to say the current level is 100%, because remember we said we have to satisfy all of the demand. I'm going to step it down by 1% increments to 99, 98, all the way down to 95% fill rate at the demand, because the company would not tolerate more than a 5% drop off in demand fill rate at the DCs. So our as-is condition, the baseline case, is that we have 19 consolidation points and 100% of the demand from the DCs are filled. That's our baseline. Well, if I have 6 different demand fill rates, so 100, 99, 98, 97, 96, and 95%, that's 6 of them, and I have different configurations in terms of 19 center points, 18 consolidation facilities, 17, and so forth. There are 36 combinations I have to run for this 6-month time period, okay? So these results tables will look very similar to this. This is the case. So the base case, I have 19 of these facilities, and at 100% demand fill rate, I've normalized my ratios here to the base case. So 1.00 is the total cost of the supply chain at the base case. It's very useful to take this base case and divide it into the resulting costs of all the other cases, because very quickly you can see for the same base case, as I start to decrease the demand's fill rate at the DC, in other words, they don't get everything they want. In other words, I'm shipping less. the costs start to go down. So this is telling me what? At a 96% demand fill rate at my distribution centers, assuming there was 19 of them, I am going to save 4.5% total supply chain transportation cost, because this 955 is basically saying it is 95.5% of the baseline. Similarly, as I remove the first consolidation point at 100% demand fill rate across all of my DCs, with only 18 of them, costs go up by 1.3%. 1.3% cost increase. Why did that happen again? Well, because if I had 19, I could get a solution. All 19 of them were being used. If I shut one of them down due to low volume, now the stuff that was going there in the cost optimal solution has to go somewhere else. It's more expensive to go somewhere else, because if it wasn't, it would have gone somewhere else in the first place. So by closing it down for a given demand fill rate, I'm going to see the costs increase, such that if I close 3 center points here, this 1.046 value, I'm saying that I have a 4.6% increase in total supply chain transportation costs if I close 3 consolidation facilities. What this model doesn't have, which we're not asked to build, but they have to consider for themselves, the client has to say, okay, how much am I going to save by closing those 3 consolidation facilities? If I can trade that off and say, hey, I can save that 4.6% through no utilities, no labor costs, operating expenses, maintenance, etc., it could be useful. The reason you see infeasible here is that if I was to close 1, 2, 3, 4, 5, the 5 lowest utilized consolidation facilities, it's infeasible in that there's not enough capacity in the entire network to fulfill all of the demand at all of the DCs at 100%. I have to go down to a 96% fill rate at the DCs in order to make 5 consolidation point removals feasible. So this type of two-way sensitivity analysis is hugely powerful to the company, because what they're looking for is where are the values right around 1 potentially. Oh, so here's a case where if I can tolerate a 3% reduction, get 97% of what I need at my demand at the DCs, I can close 2 consolidation facilities and really not see a cost impact. Could be good. Well, what's the cost impact of going down to 97% fill rate at the distribution centers? That's another thing that has to be considered here. But by using this optimization model and closing facilities and letting it reroute and redistribute the freight by different modes through different lanes, different origin destination pairs, who's on rail, who goes to the truck, etc., we're able to provide them a very nice strategic outlook with regard to the trade-offs between fill rate and the number of facilities that are open in terms of this global supply chain network here. And again, 1.00 is the base case here, because these values are the ratio of whatever the resulting cost was divided by this baseline. What about expanding these consolidation points? Well, we had to look at them, how many current dock doors there were, and what they could be expandable to. So that you can see, for example, 6910, it has 17 doors, and it can be expanded to 17 doors. That means it's not expandable, so it can't be a candidate for us to look at. So we needed to see which of these facilities have freight that are very fully utilized and can be expanded. So maybe 6935, because it has 50 dock doors, but there's room to double the size of that building basically, such that we could take it to 100 doors if we wanted to. So we wanted to ask, and the client gave us predetermined scenarios as to which CPs to look at for expansion. So if I look at this, if I was going to expand it, why not take it to its maximum capacity? Well, if it's at 50 and it could go to 100, we decided to say, you know what, we'll also look at the midpoint. So while there's definitely some cost to expanding it, if it's at A and it can go to B, We also want to take it to kind of the middle between A and B, if you will. So this one I talked about, 6935, and that's at 50. It can go to 100. We'll look at the 50 and the 75 and the 100 door case. The client knows the cost to expand it. It might be that the cost to expand to 75 is more than half of the cost to get it to 100. So it may not make economic sense, but they asked us to provide them a variety of scenarios to look at these expansions. We wanted to look at individual CP expansion as well as jointly expanding them, because as we look at our supply chain network and we expand a given consolidation point, by expanding it, if it's already fully utilized, the optimization model may want to send more freight that direction, may want to route more stuff into it because it's cost advantageous to do so. We also could look at the fact that you could expand some and close others so that the low volume areas could be consolidated, contracted down, but we could expand some others that the network balance can still be maintained. Could be that you could close 3 of them and expand 1. Could be a net sum gain of 0 total cost, but the network could like it in terms of transportation savings. So these kinds of trade-offs are letting us use our model to analyze real scenarios that the client found important. So if I look at each individually, here's a specific CP where if I close nothing and I expand it from its base to its max or the halfway value, I again have, for the 100% DC fill rate case, my normalized values. What does this mean? This means if I expanded this one CP by 15 doors, the total transportation cost would only go down by 0.001. I would guess the cost to expand that one is not small, and the savings here on transportation are not that big either. So let's start looking at, all right, what if I was able to close a CP? Close 2, close 3 while expanding. Well, here you can start to see the costs escalate. The fact is, we have not factored into this the savings from closing a CP. We have not factored into our results the costs of expanding. These, again, are minimizing total supply chain transportation costs. The client can use this knowledge to figure out, based on their estimating and their construction costs and closing costs and savings from utilities and personnel, like I mentioned, if this trade-off is worthwhile. What about a different one? Well, here's the case where we have one that can go from 50 to 100, and we look at the same closings in terms of the ones that are the least utilized, and do another analysis to say, all right, how do these cost changes? And so these look pretty similar, right? Not too much of a difference here. What if I expand them simultaneously? What if I close and do both of the expansions? Again, with our model, we can run all kinds of scenarios, and this was the importance of getting it to be tractable or usable. The fact that I can run all these cases in 30 minutes each means in a single day I can run 48-ish cases rather than needing 24 hours to analyze a case. So we're able to run a variety of scenarios and show them different cost ratios for their consideration. What about opening? Well, we look at our current results, we figure out that some locations in California are getting slammed with demand. We also see that in the Northeast, we're getting slammed in New Jersey. Well, we have some cases where they're getting slammed, they're 100% utilized, but they can't be expanded. We could have some stuff that's far out on the West Coast. If you remember the original picture, there was 2 locations sitting out in California. They're fully utilized. They handle the majority of the freight for the West Coast, and they're fully utilized at 100%. So this is kind of motivating us to say, all right, do we need more capacity in these areas potentially? Can they be expanded? If they can't, what can we do to remedy that? So we did a focused California study. We found a facility that was at its maximum capacity with all 124 doors. Another facility at 50 doors could actually be expanded to 80. So we looked at expanding it to 80 doors by varying that DC fill rate. We also wanted to look at what if I could build a new one that could have 100 doors at the same location. So we have the 50. Now this CAI facility was a leased facility, so it couldn't be touched. What if we could expand to 80 or knock this thing down and build a new one that has 100 doors? How would that help us? We ran those analyses. So here's the case where you can see if you could build a 100-door facility, we actually can get this ratio under 1 in terms of transportation costs, because now we have more capacity on the West Coast. We don't have to ship things through inefficient or more costly options. But again, these are transportation cost ratios. They have to be traded off with the savings from closing. Now I realize there are some costs with shutting down facilities as well, but also the costs definitely for expanding or constructing a new facility. We looked at the Northeast. We said, okay, here's 2 CPs. We could consolidate them. We can consolidate them and build a new facility at either of the 2 locations. We're saying we already have the site picked out. We already own it. So what if we shut them both down and build a new one where 6927 is? Or shut them both down and build a new one where 6938 is? Based on the client's statement of all new CPs will have at least 50 doors with a maximum of 100, we're looking at, again, the 50, the 75, and the 100 dock door options. So here is, at the new 6927 location, again, which ones we could close. We add the first one that we're closing. There is no 19 here because we're definitely going to close the other one. This is all in the Northeast. So New York and Pennsylvania here, fighting it out. Again, looking at different options for how the cost changes. Well, these values kind of high. Look at these. So if you were to look at these results as an industrial engineer, you can see that there's really not much variability, not much change as I build more and more doors. These are all consistent here. Similarly, these are all consistent. But comparing them, 1.07 to 1.04, 1.05 to 1.03, this 6938 appears to be the better option, right? Because for transportation costs in the supply chain, if I was to close them both and consolidate, well, if I close 6927 and built the new CP at this one facility, it looks like on average it's about a 2+% savings in supply chain transportation costs. So through this Northeast study, we were able to say that it's more cost effective in terms of supply chain transportation costs to locate the new facility in New York instead of in Pennsylvania. Maybe geographically that makes sense due to be able to reach up into Maine, reach into other states. But our optimization model was used to make these type of strategic decisions for this company. And based on that lack of variety in the cost, when we had 50 doors or 75 or 100, we said, you know what, you should just build it with 50 doors. There's no transportation cost gain. There's no savings for building more than that. Because over 50 doors, it's not going to be utilized. It only needs the demand capacity capability to handle 50 doors worth of volume. Now, maybe over time, demand in that area of the country grows, and you can expand it. But for now, our initial look said, put it in New York, shut down Pennsylvania, and build it with 50 doors, and it looks like the best approach for this type of Northeast study analysis. So let's look at the 5-year analysis. These were all kind of points in time. Well, the current network suggests that they were utilized at about 83%. So all of their 19 center points, all of their consolidation facilities were about 82% loaded across the board on average. A volume, a weighted average based on the weight of freight that it was handling. Well, the client said we expect a growth rate of 10 to 12%. So if that's the case, and we built this initial 6-month data file for the first 6 months of this year, we could take an expected annual growth of 10 to 12% and scale it down and build the next 6-month demand scenarios. Now we're assuming the product mix is going to stay fairly consistent. Because remember, this optimization model, it's a deterministic study. We don't have probability distributions here. But we could sequentially optimize each 6-month period by growing the demand at their established growth rate. We could run different growth rate scenarios based on sensitivity analyses as well. Because we have this model, why not exercise it? So we did that. If we look at the first half of the year, well, this is our baseline, right? This is about the 2.1 billion pounds of freight. And as the model elapses over time and we increase the freight by our growth rate, we start to see the cost in the network relative to our current cost. Now, we would expect the cost of transportation to go up as we flow more goods, right? I mean, such that in 5 years, we're looking at transportation costs in excess of 66% higher than today. This has nothing to do with the cost of fuel either. This is just based on our current assessments of trip miles cost or fixed miles based on the distance. Interestingly, we were able to show them that over 5 years, with decisions to make changes in the network strategically, which CPs to expand, we were able to show that we could handle this demand. Now, right here at the end of year 3, it gets pretty full. We're at 98.5% utilized. Well, then we do some expansions and it drops us back down. We keep growing. Well, right here, we need to do some additional expansions. So we were able to sequentially show them in this 5-year growth scenario how you would handle what you would have to change in order to make it feasible from a strategic study to handle this projected increase in the volume of goods flowed in the network. So our study said that there are 8 locations that need to be expanded over the next 4 years in order to accommodate this growth. We leave you at 98.8% utilized. So if it keeps growing, we're saying we looked at a 5-year scenario, but you absolutely better be realizing that in year 6, you're about to be out of room. So you might want to look a little bit further into the future. And through this type of strategic study, that helps us make better conclusions that will hopefully give them a vision of to what their future looks like in terms of this optimization model. And, you know, the second half of year 5, so period 10, we only had 2 center points that were not 100% utilized. So there's very little capacity left in this network. So if we're intending to grow at the rate they projected, they need to be wary or cognizant of that in the future. Now, we also recommended, and we did run, other cases besides this growth rate of 10 to 12%. I mean, you want to run low, medium, and high, right? Maybe we run an 8%. Maybe we run a 6%. Maybe we run a 15%. With the model, we can do these what-if scenarios and give them the range of possibilities. So finally, the last thing we did, which I thought was pretty cool, is we said, all right, what does the network really want to do in terms of what I'll call the network equilibrium? What I mean by that is, if I could have as many dock doors as I wanted at every one of these facilities, now these facilities are located currently where they are. I'm not going to move the facilities. But what does the supply chain optimization model want to do if I removed my capacity restrictions of the dock doors? So if I assume each consolidation point has infinite capacity, so we just put in they had 10,000 dock doors. You know, you can't really put infinity into an optimization model, but you can make the number so large that the entire network's demand could go through each one of the CPs. The model will figure out then where it would like to go to minimize total transportation costs. So that idea is what I'll call the desired operating state. If I truly had infinite capacity, then I can make sure that only my transportation lane restrictions by mode and the fixed and variable transportation costs are the only thing that are impacting the decisions the model makes. There's no capacity limitations at the consolidation points. So if this was the case, if I was allowed to do this, we were able to look at all 10 periods and basically show them over time how the model wants to handle the changes in demand growth with its desired operating state, to kind of tell them, you know, you might have given us an input where this CP has 50 doors and it can expand to 100. But our optimization model with this equilibrium could say that, you know what, I'd like 500 doors there. I'd like 312 doors there, because it's in such a great location with the way that the supplier and the 3-digit zips flow goods to the distribution centers, This is really a key node in my network, if you will. Or, here's an area that I don't need hardly any dock door capacity because I really don't want to have to use it. If you gave me the capacity I wanted at the desired locations, I could shut down a bunch of other center points. So through this kind of network equilibrium study, one of our last analyses we did for them, was able to show them how the natural gravity of things would want to work if capacity was not an issue, which is also another eye-opening way to realize where the important or more important parts of a network are, where is really being constrained, kind of focus our areas for future improvement. So in the next lecture, I'm going to finish up this little module with a discussion of the simulation modeling we did for an individual consolidation facility, because we just did this 5-year strategic study, and we planned out network locations and distribution and routing to minimize transportation costs. But now we take it down to a lower level, and at simulation, look at the dynamics inside of a consolidation point to see if, as demand comes in over time, that we're going to characterize with a probabilistic distribution, can we get it through the facility and properly processed within the 48-hour desired turnaround time inside the facility? So with that, I bid you good day.